Welcome back, dear students, to the tetrahedron chemistry classes. So in today's class, I am extending that thermochemistry lecture to a little bit extent. Okay, and today we'll discuss heat of combustion only. In the earlier class, that is in my first lecture of thermochemistry, I have explained you the concept of the heat of formation or enthalpy of formation along with the numerical involved in it. Today I will extending this particular topic to the heat of combustion only, right? And this heat of combustion is very useful again in deciding the heat of formation of various compounds. Okay, so what is by definition, what is heat of combustion? The heat of combustion of a substance is the change in the enthalpy of a system when 1 mole of a substance is completely burnt in excess of air or oxygen. Remember, it is for 1 mole only, right? So whatever the compound you are having, generally you will have the organic compounds, because organic compounds contains the carbon and nitrogen, and they are combustible. Combustible means when you have the sufficient supply of the air, then you can burn that particular compound because it is having the carbon and hydrogen, right? This you know. And because I'm dealing with the enthalpy of combustion, so conventionally, basically, enthalpy of combustion is denoted by delta H C. Okay, so this is the definition. So how you can understand the concept? Say for example, you are having this molecule of methane, okay, and in the sufficient supply of oxygen, right? So whether you have the sufficient supply of the oxygen or the air, because air contains oxygen and oxygen helps in the combustion, right? So whatever the composition is there, only oxygen will be helpful in burning the compound. So that's why it is written in excess of air or oxygen. Okay, so what will happen whenever your organic compounds burns? You will always have only two compounds. First is your carbon dioxide and second is your water, okay, in the form of the vapor. So this is your gas, and this oxygen is also gas, this carbon dioxide is also gas. Of course, this water will be in the vapor state, but it will be condensed to the liquid. Okay, and for this heat of combustion, that is delta H C, the value is negative 212.7 kilocalorie per mole. Please remember the unit is the kilocalorie per mole, and remember this value is negative always, because all the combustion processes are exothermic in nature, and for exothermic reactions enthalpy change is always negative. So your heat of formation may be your positive or negative, but heat of combustion will always have the negative sign. Please remember, this is very important. Okay, let's take another reaction. Say for example, you are having carbon in the solid state, okay, and then you are reacting it with the oxygen, but the supply of the oxygen is limited. So I'm writing here limited supply. Limited supply means there is no excess of the oxygen. So again the reaction will take place, and you will have carbon monoxide, and along with the carbon monoxide, okay, so you will have the carbon monoxide as the byproduct, because you are burning this carbon only. Change in the enthalpy would be there in this case again, right? The value is negative 94.3 kilocalorie per mole, but you cannot take this particular value as heat of combustion because combustion is incomplete. Please remember, whenever the complete combustion of the organic compounds take place, your carbon dioxide is the main product, and when the combustion is incomplete, then carbon monoxide will be the product. When the combustion is incomplete, then this cannot be your heat of combustion. This is something very important. Okay, right. Applications of heat of combustion. First of all, calculation of heat of formation. In the last class, I have already told you the concept of the heat of formation. That means the formation of a particular compound from its constituent elements, right? In this particular process, whatever the enthalpy change is there, that would be termed as your heat of formation. So indirectly, when you have the value of heat of combustion, then with the help of the values of the heat of combustion, you can calculate the heat of formation of the compound. This is one of the very important application. Okay, And then calorific value of the food or the fuel. So whatever the food we will take, it will convert into the energy, of course, in the form of the glucose. Okay, and then this will convert into the ATP, which is the energy currency. Okay, but I'm not going into the detail of the food chemistry or the biochemistry, but I'm telling you calorific value. Your food may have the calorific value, your fuel may have the calorific value, and calorific value is nothing when you burnt 1 gram or 1 volume of any fuel or food. Whatever the amount of the heat will be produced, that heat will be termed as calorific value. Okay, and the unit of calorific value is always per gram. Either it is calories per gram or kilocalories per gram or kilojoule per gram, like that. Okay, so by definition, calorific value is defined as the amount of the heat produced when 1 gram of the food or the fuel is completely burned. This is the definition. Okay, so let's take one or two example of this. So for example, I am giving you this equation again. Your methane gas, okay, it is a fuel reacting with your oxygen gas in the sufficient supply, and you are burning it, and you will have carbon dioxide in the gaseous form, and then you are having water in the liquid form. Okay, and for this heat of combustion, I already told you the value is negative 212.7 kilocalorie per mole. And if you convert that kilojoule per mole, so this value would be negative 890.3 kilojoule per mole. Okay, I hope you know the relation between kilocalorie and kilojoule. So I'm telling you here, 1 kilocalorie equals to 4.184 kilojoule, right? This is very important relation. And now say suppose you are having next to your compound, say you are having C2H6. This is your ethane gas. Okay, and you are reacting it with the sufficient supply of the oxygen O2, and then you are forming your product, and products are always carbon dioxide and water. If you want to balance this particular reaction, then definitely 2 of the carbon dioxide would be there and 3 of the H2O would be there. Please remember, it is gas, it is also gas, it is liquid. If you balance this particular reaction, you can see here 2 to the 4, 4 oxygen and 3 oxygen there, 7 oxygens are there. So you need 7 oxygen atoms. So you can write it as 7 by 2 of oxygen, right? This will make sense. How? See, this 2 and this 2 gets cancelled and you left with only 7O, and in the product side we are having 7 oxygens, 2 to the 4 and 4 plus 3 7. That's why I have written this one. Okay, and heat of combustion for this particular reaction is negative 1559.7 kilojoule per mole. Okay, so this is the heat of combustion, right? But we need calorific value, and calorific value we always calculate for 1 gram. Okay, so if you calculate the calorific value for this one, let's calculate the calorific value. So I'm writing that is heat produced by the 1 gram of the fuel or the substance. Okay, and this is where, say, if I go back previous slide, this value for methane is 890.3 kilojoule per mole, and we need to convert this per mole into the per gram. So to convert this into the per gram, you will take this value here, which is where 890.3 divided by molecular weight of the methane, which is 16. You know, your methane is CH4, carbon is 12, hydrogen is 1 times 4. This will give you the 16 AMU is the weight for this particular compound. Okay, this is the molecular weight, and you will write this 16 here and 890.3. But the very important thing which you are noticing here is that earlier you are having this negative sign here. Okay, and here I have omitted that negative sign. Why? Because calorific value cannot have negative value. The value of the calorific value is always positive, and it is only the convention of exothermic reaction where you take the negative sign along with the enthalpy change for heat of combustion. But when you calculate the calorific value, so you will omit that negative sign, because calorific value is always in positive plus sign. Okay, and if you solve this, then this will give you 55.64 kilojoule per gram. Now we have converted this into the per mole to the per gram, and same thing you can do for the ethane as well. Okay, and for ethane I am writing here, the value was, let's go back, 1559.7. so I'm writing here 1559.7, and the molecular weight of your ethane, which is where C2H6, carbon is 12 times 2 plus hydrogen is 1 times 6. Okay, and then this will give you 30. Okay, 13 AMU is the molecular weight of this ethane. So for ethane you will divide this value with 30. Okay, and then you are having the value which would be your 51.90 kilojoule per gram. Okay, now you can see here this value is 55.64 for methane, right? And for ethane this value is little bit of lower side, that is 51.90. It clearly indicates that methane is a better fuel in comparison to the ethane, because ethane's calorific value is low, 51.90, and methane calorific value is high, 55.64. And by definition, or by the concept, you know, the fuel which will give you the higher energy, right, that will be your better fuel. That's why this methane is the better fuel. I hope this is clear to you. Calculate the standard heat of formation of propane if its enthalpy of combustion is negative 2220.2 kilojoule per mole, and the delta HF, that is heat of formation of carbon dioxide, is negative 393.5 kilojoule per mole, and heat of formation of liquid water is minus 285.8 kilojoule per mole. Okay, so you need to calculate the standard heat of formation of the propane. So what is the required equation, what you need actually? Okay, so your requirement is what? You need 3 of the carbons, okay, plus 4 of the hydrogens, and if you react them, then you will have C3H8, and for this you need to calculate delta H standard F, this particular value. Okay, this is your required reaction. I am writing RR, where RR stands for the required reactions. And what you have been given? You have been given this value, heat of combustion of propane. Okay, so what is the heat of combustion of the propane? So you are having C3H8 and you are combusting it in the sufficient supply of the oxygen. You know, you will produce your carbon dioxide in the gaseous form and your liquid water. L I am writing for liquid water, for gas I am writing G here, and this is G. Okay, if you balance this particular reaction, so you will need 3 of the carbon dioxide and 4 of the H2O, and then you will write here 5 of O2, right? 5 to the 10 oxygen atoms, 3 to just 6, and 4 1 4, 6 4 10. So right hand side and the left hand side you are having the 10 oxygen atoms. That's why I have written 5 here. Okay, and for this combustion you have been given the value delta HC, and the value is negative 0.2 kilojoule per mole. Okay, this value is given to you. Now your next reaction is what? Heat of formation of carbon dioxide. So how we can form the carbon dioxide? Okay, carbon in the solid state, oxygen is O2 in the gaseous phase, and then it will produce your carbon dioxide in the gaseous phase, and for this your delta HF is given, and the value is negative 393.5. Again, it is kilojoule per mole. And next is what? For water molecule. So how we can form this water molecule? The third reaction, you'll write say H2 plus half of O2, and this will form H2O in the liquid form, and then delta HF is given for this reaction as well. This is negative 285.8 kilojoule per mole. Okay, these data you have been given. Say for example, I am writing this equation as 1 and this equation as 2 and this equation as 3, and this is your required reaction. You can see your required reaction is having 3 carbons. Okay, so that means you need to multiply your equation 2 by 3. When you multiply it by 3, only then you will have this particular 3 of the carbon. So here I am writing multiplying, sorry, I need to change the color. So your equation 2 multiplied by 3. So when you multiplied it by 3, and I'm calling this equation as equation number 4. Okay, and if I go back, I can check the data. For this particular reaction, the value is negative 393.5. So you need to multiply this value with 3, because you have multiplied entire equation with the 3. So its value will also be multiplied by 3. Okay, so for this reaction, you can write here negative 1180.5. I am writing the kilojoule here. Okay, it is not per mole, because you have been using now 3 moles and the 3 moles. Okay, so per mole will not be there, right? So this is how you can get your 3 carbons. If I go back, you see in this equation you need 4 of the hydrogen, but here this equation number 3 is having what? Only 1 of the hydrogen. So you need to multiply your equation 3 by 4. So I'm writing, so when you do this, you will have your next reaction. 4 of the water molecule will form. If I go back, you see this was your H2. You multiply it with the 4, this will become 4H2. Half H2 is there. If you multiply with this 4, okay, so 2 to the 4, you left with the 2 of the oxygen. That's why I have written only 2 oxygen over there. Okay, please remember, it is very, very important. And the value is 285.8 kilojoule per mole. So again, you will convert this. Say for example, I am calling this as equation number 5, and for this equation number 5, you are multiplying this value negative 285.5 multiplied by 4, and you are getting negative 1142 kilojoule only, right? This is how you have created these two equations. Okay, now what you can do, you can add these two equations. Why I'll add this equation 4 and 5? Because you can see here, in the required equation, I am having 3 carbon and the 4 hydrogens, and in my equation number 4 and 5, I am having 3 carbon and 4 hydrogen. If I add these two equations, only then I will have the 3 carbon plus 4 of the hydrogen, right? That's why I am adding these two equations. Somehow we need to get this particular equation. Now, which equation? Yes, this particular equation. Somehow we need to get this one. Okay, and see, this is the only point where you will find these particular numericals little bit difficult, because you have to generate that equation by manipulating the equations. Okay, so what I am doing, I am adding this. So I am writing it here just like that. I am adding these equations. So I am putting plus here, plus here, and plus here. Okay, and then you will have your 3 of the carbon in the solid state plus 4 of the H2, the gaseous state, plus 5 of the oxygen in the gaseous state, and this will form 3 of the CO2 in the gaseous form, and then your 4 of the water molecule in the liquid form. Okay, and then what you will do, you will add these value as well. These value you will also add. If you add this, 0.5 is there and 2 is there, 8 or 4, 12, 12, 2 carry 1, 1, 1, 2 and 3, and then 1, 1, 2, 2, 3, 2, 2.5 kilojoule you are getting. Of course with negative sign, right? This is you are getting, and say you are calling this equation as the equation number 6. This is say your equation number 6. Now what you need, see, you only need in your final equation 3 of the carbon, 4 of the hydrogen only, and of course here this particular propane which is not there in this particular equation. How we can get this propane included in this particular reaction? I need to incorporate this particular reaction, equation 1. So what I will do here, equation 1 is propane 5 of O2, 3CO2, 4H2O. I will write this again here. Let's go back. Value is negative 2220.2. Delta H equals to negative. And then you are having this particular equation. So I'm writing this equation here. 3 of the carbon solid. So I'm writing both the equations here. The equation was, you see, 3C. This is your equation number 6 plus 4 of H2 plus 5 of O2, and they are forming 3 of the carbon dioxide and 4 of the water molecule. Okay, and the value was delta H equals to negative 2322.5 kilojoule, right? This was the value, and your equation number 1 was C3H8 plus 5 of O2, and they are forming 3 of carbon dioxide plus 4 of H2O, and for this the value of delta H is minus 2220.2 kilojoule. Okay, and then what I'll do, I'll subtract these equations. So for the subtraction, I need to put minus here, minus here, minus here, minus here, and this would be your plus now, because earlier it was here negative. And then you can see here minus 5O2 plus 5O2 will cancel each other, 3CO2 plus minus 3CO2 will cancel each other, minus 4H2O and plus 4H2O will cancel each other, and finally you will left with 3 of the carbon combining with 4 of the hydrogen molecules minus C3H8. And if you rearrange this particular reaction, this is 3C 4H2, and then I'll take this CH3H8 and put on the right hand side of the equation, then this negative propane will become positive propane, and if you do the subtraction for these value, okay, so this will become minus 102.3 kilojoule. So this is your answer. Okay, so you see the how important your heat of combustions are, because with the help of the heat of combustions we can calculate the heat of formations of various compounds, for which you cannot go for the direct determination of or direct calculation of the heat of formation. Okay, I hope you understood the lecture. If you understood it, please like the lecture, and if you're watching video for the first time, please subscribe the Tetrahedron Chemistry classes and do share with your friends as well. And I'll meet you in the next lecture with the say heat of neutralization. Okay, so that's it for today. Thank you very much.